Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're going to have a fantastic keynote by Win-Mei Wu, who is Walter Sanders AMD Chair of Electrical and Computer Engineering at the University of Illinois. He has a PhD from the University of Berkeley, California, Berkeley, and he has received many, many, many awards for his work in architecture and software for HPCs. He received the 1993 Eta Kappa Nu Outstanding Young Electrical Engineering Award, the 1994 Xerox Award for Faculty Research, and many other awards. He's going to be talking about high-level programming in many cores. Please help me to welcome him. Thank you.
Thanks. Thanks, Juan. Thanks for that extremely warm introduction, but I hope I can live up to the person you introduced.
Yes, we cleared up the noise, so.
Okay, so this is really a lunch talk. So I promise no compiler, flow analysis, no dependence analysis, no equations, and anything else you want me to take out, I will. So what I like to do is to give you a little bit of a journey of how we're dealing with engaging people who are actually doing many core programming today, and what are the kind of things that we believe will have to be technologically advanced in order to really help these people. And so the work involves a lot of people, and this is the picture of the UPCRC Illinois team, and there are 17 faculty members. Many of them are here, so I see many, many faces here. And so there are a few aspects that you will probably get even better treatment about the subject by talking to them this afternoon. So instead of taking a nap after lunch, you should go to the sessions or talk to some of my colleagues. So the vision is for UPCRC Illinois is to make parallel programming easy, and we're going to especially want to focus on simple programming patterns. And there will be some very, very hard problems. And we believe that if we help people to solve the simpler problems first, then we have a chance of attacking the harder problems. Right now, I personally believe that a lot of these problems have to do with the tools not being able to engage the real development process and workflow and people's real needs. So the topic says many core. So I'm just kind of going to quickly go over what I mean. What I mean is the kind of processors that will have limited resources, very limited resources. Mostly the resources will be dedicated to the compute units, so you have lots and lots of them. And then you will have relatively small amount of control. So in some ways, it could be a CPU that is kind of in terms of reduced core complexity, or reduced amount caches, or GPU today. You will see typical examples of these many core types that I will be talking about here. So the first thing we learned about many core is it only makes sense to program these many cores if you care about performance or scalability, or both. So if you don't care about either of those, you really should save your time. And if you just write a very simple piece of code, chances are it will run better on the CPU. Okay, so don't bother with that. And the other lesson we learned is that performance on a single chip versus scalability across different chip levels actually share a lot of the same techniques that people need to use. So in many ways, the first order effect of getting performance on these chips is to make sure that your program is scalable. And the techniques that I'm going to be talking about that many of these developers wish we could help them with fall into that category. And then there are some detailed performance tuning some, fairly fine-tuning kind of things that you can do, but those are in general second-order effects. So, many people will even tell you from some of these vendors that it may or may not even be worthwhile trying to do some of those kind of fine-tuning even for a particular generation. Okay? So what I would like to convey to you is today there is a major gap between the programmer's need and what the tools actually are doing. Okay? And it's our job, people in this room, to be able to fill that gap and being able to empower these people. Okay? So there are three important things that almost every many core programmer will tell you that, okay, if they're successful in doing what they do, they will tell you there are three things that in general they probably did right. The first one is you need to have massive parallelism in your application. If you don't have parallelism, it's not going to be good. So in general, people are finding most of that in the data parallelism today. Okay? And the second one is regular computation of data accesses. You will need to be able to somehow either have some kind of regular application or regular data set that falls on your lap, which means you're lucky. Or if your application algorithm or your data is not quite regular, then you need to work hard to regularize it. And regularization is actually something that is, that is going to be the key in this whole game. By regularizing things, you also create similar work and avoid loading balance. Okay, and I'm going to show, I may not even show you some data because it's a lunch break, but the loading balance or data, uniform data distribution can really make a huge difference in terms of performance of these devices. And then they will finally say, well, a lot of my time is spent on two smaller things. One is DRAM bandwidth. Okay, and it may appear like a small thing, but that's probably where people spend most of the time today, trying to optimize the data access patterns and use the on-chip memory to cut down the amount of bandwidth demand that applications are putting on the chips. And then the DRAM system. And the second one is a little more subtle, conflicting updates to memory locations. And a lot of the straightforward parallelization involves atomic operations, critical sections, and these things in general destroy the scalability of these algorithms. So a lot of the work is actually in turning their algorithms inside out, changing some of the, replicating some of the states so that you can avoid that kind of situation and then get scalability and oftentimes performance. Okay? So, you will say, well, is it really the case? In general, maybe a few years from now, people will be building hardware that, the regular data accesses will not be important. Maybe Intel will figure out a way to build some kind of magical hardware that, the memory bandwidth will no longer be a problem. And, I sure hope so. I'm a computer architect as well, so, I would like to be part of the team to build that magical device. Okay, I really would love to. So if Intel comes to me and say, here's a piece of technology and fabrication technology, can you come head up this team and you will build that magical device? I will quit my university job and join Intel today. Okay, put it this way. So, but if history makes any sense, it tells us that whenever you want to manage a massive amount of parallelism, you do need to have some kind of regular usage pattern. Otherwise, it's not going to work. Whether it's military on top, Army, Navy, Air Force, or manufacturing, agriculture, this is close to my house, the second one. And banquet, have you ever been in this large banquet where the chef says, please let me know exactly how you want to customize your food? You're lucky that the chicken gets to you while it's still warm, right? So that's what latency and regularity means, right, in large-scale systems. And this is a picture probably taken not too far away from this location, on the left-hand side. For those of you who had to, come from the airport around maybe 5 o'clock, you know what that picture means. So, but you know what? Whenever the cars can maintain some kind of regular pattern, everyone can progress. Whenever you start to have some A-name people going like zigzag like this, and then people start to hit their brakes, you see what happens to the traffic pattern, right? You start to see stalls. So that's why, I'm relatively, pessimistic about the possibility of eliminating some of these regularization techniques that people need to use in programming these many core chips in the future. So there are a few things that you need to, you need to overcome in order to get to success. Serialization due to conflicting updates, oversubscription of critical resources, and load imbalance. Bad things happen when you have, things where, the regularization process start to break down, and, you start to have irregular, congestion. So, what are the things that people need to do? I ended up doing something pretty stupid in the past three months. I agreed to edit the first 2 volumes of GPU Computing Gems. So we ended up with almost 300 submissions, and we carefully read through, all the proposals, and then picked about 110 ones that we believe are reasonably successful, that people have, been successful in doing their applications, and they presented a case of how they reach success, some kind of recipe, some kind of, repeatable, description of what they did. Out of the 110, when I read through all the work, I started to realize that they invariably go through pretty much the similar process. They, in general, need to understand the relationship between the domain problems and computational model. That's one thing, the first thing that, that jumps out. There are many, many different models for doing the same kind of, goals, right? In the science, in the engineering, in the video processing domain, and you need to understand that level. The second one is you need to understand the strengths and limitation of your computing devices. Very few authors who have some kind of, erroneous description about the strengths and weakness of the chip will ever be able to get performance out of them today. And the third one is implementing those models to steer away from the weakness. So essentially, they're practicing techniques needed to translate from undesirable patterns to desirable patterns. That's all it's about. And one of my former students, said this to me. He said after he finished his thesis, I said, what did you learn, John? And John said, boy, we never solve any problems. We never, ever solve any problems. We push the problems around to places where they matter less, right? So it's all about pushing some of these things into the, under the carpet, or, or around the corner where no traffic is there, and, they don't matter that much. And then you start to get real performance out of these things. So let me kind of, comment on, a little bit philosophy here. This is a slide that, from David Patterson, and he cited, a fairly widely known, 7 dwarfs. And there's, initially there's 7 types of computation, and structured grids, unstructured grids, fast Fourier transform. Even though Dan said yesterday that FFT is not an application, but it's a very important component of every application. Dan, sorry, to me it's still very important, and I'm still learning something about FFT every day. So the point of using this is to say, we have a reasonable framework for this particular taxonomy to understand the general types of applications, or the general types of data structure or computation that people do. But what this one doesn't teach us is exactly how people are getting performance out of all these types of applications. From my experience, there is a small set of techniques that people can use to get good performance out of all these types of applications. So this is what I call the 7 techniques in many core programming. And the first one is scatter-to-gather transformation. The second one is granularity, coarsening, and register tiling. Third one is data access tiling for locality. Fourth one is data layout and traversal ordering to get better access patterns. And binning and cutoff, bin sorting and partitioning for non-uniform data when your data start to behave badly. And finally is hierarchical queues and queues and kernels for dealing with dynamically changing and dynamically generated data. Okay, so after reading through all the 110 chapters, I started to say, okay, I can map pretty much what everyone did in all those works into a subset of these 7 techniques. So good. So at least we have something here. So what I'd like to do is to give you a little bit of sense of how these techniques are actually being used by real programmers. But the point is, I would like to get you started thinking, and hopefully I will also give you some good indication of how the future tools, how the future languages will fit into this kind of workflow. Okay? So the first one is scatter-to-gather transformation. Whenever you have a quadratic kind of computation where you have lots of input, you have lots of output. And each output is going to be affected by some significant number of input. That's how you get large amount of computation time out of a lot of these calculations. It's oftentimes very convenient to express your computation in terms of inputs. That is, given each input, what are the outputs that should be affected? There's a good reason for this. In most of the engineering and science computation, the output tend to be more regular than the input. Okay, whether it's many n-body problem where you're calculating some kind of force grid, whether it's a medical imaging problem where you're trying to take some scanned data and generate some kind of regularized volumetric data, the output tend to be a lot more organized and regular than the input data. So that's why it's very natural to write a piece of code, say, okay, go get the next input, which will give me, the input is going to give me some kind of coordinate and some kind of value, and then I'm going to do something. And you can calculate the extent to which the input will affect the data. But in many core execution, this is a disaster waiting to happen, because that input-oriented programming is going to create these threads that will be trying to write into a range of output, and they start to trample each other. So you need to have some kind of atomic operation. But these things tend to create long latencies and waits and so on, because they just need to line up. So in general, the first thing that a lot of these people do is to convert the execution into output-oriented expression. Essentially say, every thread is going to look at one output, and it's going to figure out what are the inputs that it's going to need in order to produce the output. Easily said than done. Because remember, I said the input tend to be less regular than output. So given an output is in general not very easy to find the input. And I'm going to come back to this point. But in general, that's the first order transformation that these people tend to do. And the second one is thread coarsening and register tiling. We all know that parallel computing in general would require some kind of redundancy. If you truly want to have Clay to do something and you want to have Mike to do something, in general, you don't want them to have to communicate with each other. So if there's some little things that each one can do locally, you don't want them to communicate. You want them to just go ahead and do them personally. So I'm showing a fine-grained parallelization where each chunk is a thread. And then there, let's say 2 redundant pieces of work followed by, one unique work and then some redundant work. And you will have, let's say 12 of these threads that you can schedule into some kind of many-core chip and then just, execute them. Oftentimes, it becomes desirable to fold several threads worth of work into one bigger heavier thread, so that you can calculate the redundant work, put them into the register, a register somewhere, and then have the other equivalent threads folded into this thread to enjoy that piece of work. This essentially sacrifices some parallelism, but we all know that register access can be extremely efficient. So at some point, if you have too much parallelism, then oftentimes the real way of getting efficiency and then even scalability in some ways is to create large enough threads that can actually conserve memory accesses and calculation based on the register storage. Jim Demo's students did a register, the matrix multiplication method, which makes use of essentially this concept. And Jim, I'm not going to to give you opportunity to hit me with a hard question about that. But that's my perception of one good thing that you did. You actually created a much bigger usage of the registers so that you can conserve the bandwidth requirement from that chip. So the third one is data access tiling. And this particular method essentially has to do with the following. Once you converted your computation from input-oriented into output-oriented, then you have all this gather pattern. But the gather pattern is going to require too much memory bandwidth to get all that data in. So what you want to do is you want to actually start to create some execution phases where only a small chunk of the input data will be actively used by a large number of threads. So you would stage these, the data chunks into the on-chip memory, and then whenever you have a chunk into the on-chip memory, they will be consumed by all the threads that are waiting for that. And for dense algebra, this is an extremely effective method. If you can do this, don't use anything else as far as memory bandwidth is concerned. But it gets more difficult when you start to have ghost cells for PDE solvers, when you have ghost cells for convolution algorithms, for media processing kind of things. Then you start to, that's where a lot of the developers start to trip, because it takes actually some intellectual power to be able to figure out the real benefit of tiling once you get to that level. And that's where some of the tools will definitely begin to help. Data layout transformation. So in many data structures, we declare the data structure as a multidimensional array, and each element of the array is actually a struct. So we can just formulate that as another dimension of the array. So in this picture where I'm showing a three-dimensional array, and x, y, actually only two of the dimensions, and then I show all the elements that are in each array element, each element in the array. So we can do array of structure, layout, which is the original layout, and this tend to be a very, very good CPU layout. And I think one of the talks that CK Locke gave, alluded to this particular issue. And then you can convert that into structure of array. And in general, whenever you don't have an effective way of tiling your algorithm, such as LBM, just by converting from struct of array to array of struct into struct of array, you can actually create enough of the memory coalescing, and then in fact, so that you can conserve a large amount of memory bandwidth out of the current GPUs. And that will give you about 4 times of performance on a GTX 280 today. What you really want to do is actually what we call the tiled array, tiled array struct of a tiled array of structs, or tiled struct of array. And essentially, rather than moving all the elements all the way out, so that you essentially gather all the elements together from each dimension, you actually create these little chunks of the elements. And then you essentially repeat this pattern. And what you really do is you take part of the lower dimension of the original array, and move them into the low dimension. So this gives you a good compromise between three things. One is coalescing needs, and the other one is actually memory channel utilization in the GPUs. This gives you a way to actually spread your active accesses across the 6 to 8 memory channels in the chip today. And the third one is, if you ever need to use the same layout for CPUs, this gives you better locality because you are not spreading the nearby element, struct elements into far, such as the same elements from the same original array into far away places. They're going to be much closer to each other for CPU caching. So this tends to be the kind of compromise an expert programmer will do for something like LBM, and to a lesser degree, many other gridded applications. The fifth one is input binning. I mentioned very briefly that input data tend to be a lot less regularized than output, regular than output. So the way people deal with this problem is by pre-sorting these input data into some kind of bins or some kind of categories. They can be as irregular as some kind of spatial trees, like KD trees, quad trees, arc trees, all these different kind of tree structures. Or in some applications, when the data is sufficiently uniform distributed, you can use regular sized spatial bins. And whenever you can get away with the regular spatial bins, you don't want to go to the more exotic data structures because you have much easier access into these structures. And this is a molecular dynamic application where the force calculation has a certain cutoff distance. So for each grid point, you will have a certain number of bins that need to be considered. So if you sort these inputs into these bins, then you converted an irregular batch of data into a much more regular array structure that you can easily index and identify and create a parallel access. So that's routinely done. And then if you look at a typical electrostatic force calculation, you will see some kind of interesting tricks to avoid some of the bins by giving some exotic formula in terms of the list that you need to calculate. The consequence of not doing this can be severe. If you don't do the binning, and you start to, you're forced to look at everything before you can determine whether you need to process the input. For large data set, you can actually have, a GPU can actually run much slower than a efficient CPU implementation. But if you pay attention to binning, then you regain all the data scalability. Okay. Now, sixth one. Bin sorting and partitioning. This has to do with non-uniform data distribution. Not all the data in the real world are uniformly distributed. I wish they are. In fact, if they are all uniformly distributed, my job as a tool developer will be a whole lot easier. But when MRI people come, they will first give me some semi-uniform data, and then once we give them some good performance, they will say, oh, by the way, I have a spiral scan data that I need to be handled. And you look at this, this huge data, non-uniform distribution. So in general, the most effective way that people deal with this, those kind of data today is by taking the input data, sort them into some kind of ordered bins, and then also limit the bin size so that some of the input will fall into the GPU bin, okay, a CPU bin. And by limiting the data, then you can actually do a prefix scan to identify the boundaries of the implicit bins. They don't need to be the same size, but that's why prefix scan is such an important calculation in data parallel computing. And then, so once you define the bin boundaries, then you can load the section of the bins that are important to each thread into the on-chip memory. And as you can see, that the range could be dynamic. So you may have a situation where you may not have enough space to hold all the bins necessary for these two threads. So that's where you actually will need to default into the main memory. So in general, if you look at some of these applications, they will actually first test if the input falls in the range of the on-chip memory. If not, they go to the DRAM and then fetch the ones that cannot be windowed into the on-chip memory. And this is where you cross from a naturally organized data, okay, regular data, into an artificially regularized data, okay? And this is where a lot of the tricks are. This is where a lot of the mistakes are being made, and this is where a lot of the tools should help. None of the tools that I know of help with any of this, okay? So that's the reason why, as a tool developer, I look at this, I look at what people are doing, and I lower my head and say, shame on me, okay? I'm not tuned into that process. 7.1, when things are dynamic, like graph algorithms, like, you know what, things that are dynamically identified and say, this is my next batch of dynamic data that I need to bulk process. In general, the way to get performance out of that kind of application today is the hierarchical queues, where you use threads to produce, you know what, queued data elements at the warp level, which takes advantage of the fact that the hardware is going to be mostly, you know what, you're going to mostly have these processing elements that are active at the same time. So if you provided different queues to different processing elements, then the contention will be minimized, if not totally eliminated. So you can provide, let's say, for the current SAM for a NVIDIA GPU, you can provide 8 queues for the 8 processing elements. As they do these context switching and so on, different threads will be accumulating into the same queue, but they will be doing this in turn. However, you need to be careful, because more and more GPUs will be executing more than one warp at the same time. So you still need to use atomic operation. Otherwise, when you move into Fermi, you can actually cause problems. You can actually have bugs in your code. Now, after each thread block is done, then you can accumulate, you can actually write all your output into the block level queue. And after the kernel is done, then you can take the block level queue and then write it into the global queue. Once you get beyond the warp level and get beyond the block level, the contention will be minimized. So it's all about scalability of your dynamic assembled data. You know, how do you avoid having a bottleneck inserting the next batch of data into that structure? So correspondingly, people also have been doing hierarchical, kernel launch for these kind of applications. In general, let's say if you are doing a breadth-first search algorithm, you will start with a source, and then you will kind of grow your frontier, and you can grow into a large number of nodes. But then at some point, you may also shrink at some point, depending on your constraint. But in general, you will grow more than shrink. So at the beginning, if you are processing only a small number of frontier nodes, and you have to launch a kernel and do global synchronization, you lose all your performance. So there are usually 3 levels of kernel in these high-performance libraries. One is the small kernel that only has 1 thread block, and that uses barrier synchronization that's intrinsic in the hardware, and do the synchronization and just do the frontier propagation until the frontier grows big enough. Then they would go to the second, second tier kernel that I think Jim's students actually have been using. Essentially, you launch only enough thread blocks, which will at most equal to the number of SMs in your hardware. And then the language allows you to do a global synchronization across the thread blocks. So that will take care of about 10,000, up to about 10,000 thread, nodes in the algorithm. And eventually you'll have enough of a big frontier that you just launch a kernel every time. And then you terminate the kernel for the global synchronization. But when you have so much data to process, that launch overhead is no longer the biggest issue. So you will see this kind of pattern in a lot of the dynamic graph-oriented applications. So the reason why I talk about those 3 techniques here is really this. These tools need to fit into the workflow. This is where those are the things that most of the many core programmers spend their time. They're spending all that time trying to you get those kind of techniques done. And so the tools should help them to form efficient kernels out of these things, provide clear performance model. There should be a very clear way for them to say, oh, this is a good kernel, this is not a good kernel for my data. It should be a very easy thing to do, right? Right? And then, it needs to support software engineering when people apply these techniques. Portability. If someone crafts their kernel, with these techniques, are these kernels portable, not portable to different, targets, architectures? Testing. How do people test these kernels, once they're done? And how many times they need to test these things? And interface integrity, assumption verification. A lot of times when people apply these techniques, they actually need to make some assumptions about how the rest of the code is behaving. The pointers, the sum of the data structure, shapes, and so on. And currently, there's no way for the system to help them to enforce these assumptions or check these assumptions at runtime and say, oh, what you're assuming here is not really what's happening in the rest of the code. The legacy code is doing something weird here. You're not going to be able to do the parallelism that you want, okay? But it's not there, right? So that's why we believe that these tools and applications really need to be co-designed so that the tools are feeding into the places where people are really doing most of their work. Okay, so this leads to what we're proposing for the second phase of UPCRC Illinois. So we have three big chunks: AvaScholar, SafeSpeed, and Acrobatics. So the AvaScholar is the component where they're developing some very demanding applications. Some of them are already in the many cores, and some of them are in both many core and multi cores today. But there will be continued performance requirements out of these applications. And through the process, we are feeding these developers with the safety tools and performance tuning tools. And essentially, we're asking the same question again and again. Why don't people use the tool? Why are they spending 3 days here without any tool help? What's going on here, right? And so that we can begin to really tune into their development process. And this is a slide that Mark Sneer generated here, which I really like. It's a kind of a little bit philosophical, but I think it's a very important point. The point is, currently we have a compiler, a model where we generate different implementations of the same code. And then we have the user mode, user model where the user will generate different code versions, through that whole process of performance tuning. There's nothing in between. And whenever the user cannot fit exactly into this mode, they just get completely out of this mode and then use hand to do all these things. I really think that one of the biggest challenges is to actually provide something that can actually engage the user somewhere in the middle, so that the users will not do these things by hand totally, but then the compiler will not be have to do all the heavy lifting totally by itself. It's easier said than done. For all of us who have any kind of experience with that process, it is a very, very big challenge. So I have a few of these applications that for example, here for gesture interface, Tom Huang students already have an implementation of GPUs that is near real time, but they still have stability issues. So they can take another 10 times of performance just to get to the real stability of sensor-free gesture detection, right? So surface reconstruction work by John Hart students. Same thing. You can reconstruct. If you really want to, do good quality, reconstruction of these surfaces and so on for interactive, virtual presence, we still have a long way to go in terms of what we can do. Emotion detection. Dan Reed mentioned some of this yesterday. Detecting emotion is now based mostly on the volumetric image rather than the real, gridded surface reconstruction. So we still have a long way to go in order to get more reliable, detection of the emotions. So we organize these projects into refactoring paths, which will tap into the higher level programming paths that implements parts or whole of the 7 techniques in the transformation. And we currently only have partial implementation of the 3 of the 7. So it's not an easy task, but we're definitely making progress. And one of the things we're very excited about the project is that some of our we all understand that we're trying to be aggressive in terms of speed, power, and so on. But I think there's an aspect of safety net that has been really overlooked in a lot of the future past tools. That is, whenever people make these big brain surgery on some part of the code for performance, they really are making some significant interfacing assumptions. So when some of these assumptions are being violated at runtime, there's no one that are checking these things. It's not just for necessarily for parallelization, even for code update, even for just regular software update. There are routinely these kind of problems that prevent or cause a lot of cost later on for the software support. And we're developing a piece of technology that is checking and isolating these assumptions at runtime and minimize the debugging and supporting costs of these kind of things. So SafeSpeed project, I didn't spend a whole lot of time on it, but they really provide a good level of scrutiny over the code base for parallelism. So there's some plan actions for the sponsors and as usual. And but one of the things that we believe what need to happen in the future is not just Intel and Microsoft. We really need to begin to engage some more of the ISVs. So this brings me to the final slide here. This is a very well-known phenomenon of valley of death. You have a whole bunch of research that are very nice, and then you have some startup company doing some kind of tools and so on. But then you have very few things that you can actually take from research and successfully apply to these things. Whenever you try to get some high value kind of research into the commercial world, there is a valley of death. So what we're saying here is, yes, the valley of death will be there. Yes, some of our tools will be dead. On the other hand, the only way that these tools will be able to, some of them will make their way into the commercial world, is by giving the developers what they want. And I think we have a much better understanding for this particular domain what people want. I didn't talk about the entire domain, and I don't want to spend the rest of the afternoon introducing these other domains, but I hope that I gave you a good sense of our philosophy, our research techniques, and how we feel that these tools that we're developing will be different from the tools that people have been developing in the past 30 years. There's a different level of engagement that we're doing with the developers. So with that, thank you very much for your attention, and I will be happy to answer a couple questions. Yes.
So with all of these transformations,
Stefan, right?
Yeah. Yes. With all these transformations you discussed, there seem to be two extremes as to how to get them in there. One is to refactor the code somehow and make them explicit and expose them, and that's when you would want to have these test controls and so forth.
Yes.
The other one is to go to a level of abstraction where the developer is expressing less about the data layout and more about the algorithms and so
Correct.
forth, and then have a system underneath that transform them.
Yes.
So where in your experience, which of these two paths has been more successful, or what's your opinion?
Okay. Intuitively, you would expect the second one to be more successful and the first one to be less successful. In practice, the first one is more successful and the second one is less successful. The reason is because of the sorry state of what we're providing, people don't trust us. So they rather do all the things themselves, and at least they know what they're testing, and they're so that's the reason. But to me, you're actually pointing to a very important point. Unless we start to tip that balance, the productivity is always going to be a problem. So that's actually the key of the problem. When can we tip the balancing point for them to start to trust some of these tools, that they would start to use the testing methodology that we provide as part of the tool rather than doing the explicit test themselves. And that's going to be the real. Any other questions? Yes. Hey.
What are the architecture implications?
So a couple of things that we did learn. One is we can complain about these these hardware all day long. Every time I have I teach a course, every time I see some developers, the first thing they say is, oh, why do I need to do coalescing? It's such a pain, right? And I need to do corner turning and all that stuff. And so one thing that I think hardware people need to really decide is, you really need to communicate effectively to people. What are the things that you would not be able to do in the future? Okay, a lot of these people are still hoping that you will be able to reverse that trend. Maybe you will. If you will, come out and say clearly that you will. But if you can't, come out and say, this is something that the tools and the programmers will really have to take care of it, because that indecision in that communication process is very harmful. Okay. The second one is, I actually learned that CPUs, for any successful many-core processor, the part that the CPU does is incredibly important. So if you look at all the regularization processes, most of the techniques can only be done on the CPUs today. So there is a very important part that I think, you could put CPU and GPU into a competition mode and say, okay, whatever block processing you would do, I would do. But I think there's a low-hanging fruit where, a lot of these regularization processes are not necessarily supported by the CPUs in the most efficient way. So, that may be one of the things that, the Intel architects should take a look at. Okay. Any other questions? If not, oh, yes, Jim.
Where does auto-tuning fit into the framework?
Yes. So where does auto-tuning fit into this framework? So auto-tuning, to me, is a parameter. It's kind of an implementation, parameter setting kind of thing. So in general, if you look at all these 7 techniques, there are lots and lots of parameters that each technique will end up, in the code. So that's why I didn't list auto-tuning as part of the 7. To me, it is it's a final implementation phase where you finalize the parameters for those. Yes.
The book be out?
Oh, you mean the algorithm book?
Yes.
As soon as I go back, I'll start writing.
What is the time frame?
In fact, Juan is referring to the GPU Computing Gems books. Volume 1 is coming out in December. And we already finalized all the contents and it's in production. It does take about 4 months to come out. So there will be 50 articles in 10 application areas. And the second one will come out in June. And that's going to be the next 7 application areas plus the frameworks and tools. So there will be a total of 110 articles. And that's where I extracted some of these observations as well. Okay.
Thank you very much.
Thank you.